Hi, everyone. Thanks for tuning in. My name is Kevin Ta. I am a student at Yale University, and I'm happy to be presenting our work on simultaneous segmentation and motion estimation of left ventricular myocardium in 3D echocardiography using multitask learning. To set the scene a bit and provide some clinical motivation, cardiovascular diseases are the leading cause of death globally, the most prevalent of which is coronary artery disease, in which a full or partial occlusion in the coronary artery leads to reduced blood flow and myocardial infarction. This leads to tissue scarring, which leads to adverse myocardial remodeling, which can ultimately lead to death or major health complications. One clinically established method used to detect and diagnose coronary artery disease is through the evaluation of echocardiograms. In theory, the heart is expected to move a certain way, and any deviations from this could be a red flag and could be an indication of tissue damage. Generally speaking, automated methods for characterizing heart motion usually follows the pipeline of acquiring your echo image, segmenting out the left ventricle or any region of interest, then tracking the motion of the surfaces or meshes generated by these segmentations. Now, inspired by some work in the computer vision field as well as the cardiac MRI field, which suggests that these two tasks are quite related and can provide mutually beneficial information on one another, we apply this idea to develop a framework to combine these two tasks for the purpose of 3D echo analysis. This is an overview of the proposed architecture. In short, it is a two-branch network consisting of a motion estimation branch and a segmentation prediction branch. Both branches have a UNES-style architecture, which basically comprises of a downsampling path and an upsampling path with skip connections to combine the two paths. The weights between the downsampling paths are shared across the two tasks in order to encourage communication between the two branches. The input to both branches is a pair of 3D images, a source and a target image. The goal for the motion branch is to find a displacement field that maps these two images, whereas the goal for the segmentation branch is to find the contours of the left ventricle in each image. The entire network is trained using a composite loss function comprised of the objectives of each of these tasks. To focus a bit more on the motion branch, the motion branch is trained in an unsupervised manner, mainly because of the fact that real ground truth dense displacement fields is extremely difficult to obtain in actual clinical images. Now, how this works is, if you recall from the previous slide, the input was a pair of 3D volumetric images, and the goal is to estimate a displacement field that maps them. Well, the network itself outputs a displacement field. If we use this displacement field and morph the source image using some sort of spatial transformation operation, the morphed image should match the target image. Mathematically, the network aims to minimize the mean squared error between the morphed source image and the target image, and we denote this as LSIM, for the similarity loss. To discourage any jumps or discontinuities in the displacement field, which would be unrealistic in true cardiac motion, given that the heart moves as a single object, we minimize the squared norm of the spatial derivatives of the displacement field. Now, the shape constraint follows a very similar idea to the similarity loss. If we have a mask of the source image, the same displacement field used to morph the source image can be used to morph the source mask, and this morphed source mask should match the target mask. To encourage this, the network minimizes the dice loss between the morphed source mask and the target mask. The overall motion branch is trained in a combination of these three terms, with some weighting at each, which was empirically chosen. Now let's focus a bit on the segmentation branch. The segmentation branch is trained in a supervised manner. Ground truth segmentations were annotated manually and confirmed by a trained expert. The segmentation loss is comprised of two terms, a dice loss and a binary cross entropy loss. The dice loss measures the degree of overlap between the predicted segmentations and the manually traced segmentations. And the binary cross entropy loss penalizes incorrect labeling of voxels by the network compared against the correct manually derived labels. As with the motion loss, the two terms are weighted and the weights were determined empirically. So we evaluated our model on an in vivo canine dataset gathered in-house. The dataset consisted of 8 anesthetized open-chested canines, which were imaged under 5 physiological conditions: a healthy baseline, mild LAD stenosis, mild LAD stenosis with low dose dobutamine, moderate LAD stenosis, and moderate LAD stenosis with low dose dobutamine. Now, in terms of actually training and evaluating the model, as I mentioned earlier, our inputs were image pairs. The pairs were sampled in a one-to-frame manner, which means given a sequence, we denote time frame 1 as the source image, and every subsequent frame becomes a target image. We completely separated one entire study for testing, including all the physiological conditions. Of the 7 remaining studies, we randomly divide the pairs into 90% for training and 10% for validation and parameter sharing. We resampled all the images such that 1 voxel corresponds to 1 spatial millimeter, and then we further resized the images to 64 cubed just for computational purposes. Taking a look at the motion estimation results, we compare our model against an optical flow algorithm, which is more of a classical motion estimation approach, as well as state-of-the-art unsupervised deep learning approach. Looking qualitatively at the motion vectors, you can see that the proposed model produces a smoother and more anatomically plausible displacement field. Quantitatively, because ground truth dense displacement fields are scarce, we evaluate the motion performances by using the dense displacement fields to warp manually traced source segmentations and comparing the mean contour distances with the manually traced target segmentations. We evaluated the performance on both the endo and echocardiums. The quantitative results show that the proposed model performs favorably against both the deep learning motion-only network and the optical flow for both endo and echocardiums. A Wilcoxon rank sum test confirms significance at p less than 0.05. Taking a look at the segmentation results, we compare our model against the segmentation branch trained on its own, which resembles just a classic 3D U-net. Taking a look at the qualitative mask on figure 3, we see that the segmentation-only model seems to have discontinuities in its predictions, whereas the proposed model does not. For quantitative evaluation, we compare the Jacquard index, which measures overlap, and Hausdorff distance, which measures max distance between the 2 contours. The proposed model performs favorably against the segmentation model in both metrics, and Wilcoxon rank sum test confirms statistical significance at p less than 0.05. So in conclusion, we introduced a multitask learning framework that could simultaneously optimize motion tracking and segmentation in 3D echocardiography. We incorporated some anatomical constraints in the form of motion smoothness and shape consistency in order to enforce realistic cardiac behavior. And our qualitative and quantitative results suggest that the proposed joint model performs favorably against the tasks trained on their own. And with that, I'd like to thank you all for tuning in, as well as my co-authors and colleagues for all their contributions and efforts in making this work possible.